This is a tutorial on graphs of polynomial functions. Now when we factor and solve a polynomial function, we're finding values of x that make this function equal 0. So let's try this. We have x cubed minus 9x. If we factor out an x, we'll get x times x squared minus 9. Now an x squared minus 9 factors into an x minus 3 times an x plus 3. But don't forget about our other x, it's still out here in the front. So here we have our fully factored form of this function, x cubed minus 9x. Now to solve for x, we set this function equal to 0. So we set all of these terms multiplied together equal to 0. Now since all of these terms are multiplied together, if any one of these terms is equal to 0, then it doesn't matter what the other two terms equal, because anything times 0 is 0. So knowing that, we solve each one of these terms for 0, and we'll get x is equal to 0. We'll also get x is equal to 3, and we'll get x is equal to negative 3. Now remember, this is set to 0, this equation. And if we thought of this as y is equal to x cubed minus 9x, that would mean y would be equal to 0. And that makes each of these values we found an x-intercept, because y is equal to 0. So we would have the points 0, 0, 3, 0, and negative 3, 0. And we can plot those points. 0, 0 is right here. 3, 0 is right here, and negative 3, 0 is right there. Well, now we have 3 points, and we can almost graph this polynomial function. Let's find 2 more, and we should be able to complete our graph. If I plug in a negative 2 for x, where we have x cubed minus 9x, if I plug in negative 2, we get a negative 2 cubed minus 9 times negative 2. A negative 2 cubed is a negative 8, and then we subtract 9 times negative 2, or a minus 18. If we subtract a negative, we're really adding, so this is going to be equal to 10. So now we have the point negative 2, 10. And if we graph that one, negative 2, 10 is up here. We're almost done. Let's find one more point. We'll try a positive 2. If I plug in positive 2 for x, I get 2 cubed minus 9 times 2. 2 cubed is 8, and 9 times 2 is minus 18. So this is equal to negative 10. So again, we have the point 2, negative 10. So if we plot that one, we go to 2 and then down to negative 10, and we'll get a point right about there. That means our graph looks something like this. So what's important to realize is that these solutions that we've been finding for x are actually x-intercepts, and we can use those to graph our polynomial function. Now the next thing we have to talk about in polynomial graphs are turning points. Let's look at our first graph. This is the graph of x cubed minus 10x squared plus x minus 2. Now a turning point is just the point where the graph kind of turns around. So we're heading upward here, and then we start heading downward in the y direction. So right here would be a turning point. Then we're heading downward, and we turn and we start heading upward again. So right here would be another turning point. These turning points are called local and maximum and minimum. This is a local max because it's larger than all of the values in y surrounding it. This one here is called a local min, or a local minimum, because it's smaller y valued than any of the points surrounding it. Now notice these aren't the largest value of y on our function, because this function continues to head in the positive y direction. And then this isn't the smallest value or the minimum value of our function because this end of the function heads in the negative value in the y. That's why they're called local max or local min, because they're just larger or smaller than the surrounding points on either side of them. So let's look at our next graph. Here we have the graph of f of x is equal to 3x to the 4th power minus 7x cubed plus 10x minus 15. Well, here we have two y-intercepts, and those would be our solutions for x. And then we have three local minimum or maximums. Here is a local minimum because it's smaller than either of the points on either side of it. Here is another local minimum because, again, it's smaller than the points on either side of it. And then in the center here, this is a turning point because at this point the function stops going up and starts going down again. So this is a local minimum. This one is a local minimum. Then this would be a local max. So now let's see how we can find or use this information about graphs of polynomial functions to maximize the volume of a cylinder, say. Now the volume of the cylinder is equal to pi r squared times h, where r is our radius and h is the height of the cylinder. And we're told that r is equal to 10 minus x, and that h is equal to x. Well, if we plug that in for r and h, we'll get our volume is equal to pi times 10 minus x squared, and then times x again. So this is the same as volume is equal to pi times 10 minus x times 10 minus x again, and then times x, because this is just our square. Now if I multiply this out, I'm going to take these first two terms. We'll get a 100 minus 20x plus x squared. This is all still multiplied by pi and still multiplied by x. Now if I carry my x into the parentheses, I'll end up with pi times x cubed minus 20x squared plus 100x. So now we want to maximize the volume of our cylinder. Well, let's look at the graph of this function. The graph of this function will look something like that. Now notice on this graph, we can find our x-intercepts, or the solutions to this polynomial. They occur here at 0, and they occur here at 10. Well, let's think about what's going on. If we have an x value greater than 10, then our radius here will end up being a negative number. And since radius is a distance, you can't have a negative distance. So anything greater than 10 wouldn't make sense. And then we have another intercept here that's at 0, and that's because our height is equal to x. So if we went to the left of that x-intercept, we would end up with negative values of x, and then that would make our height negative, and then that wouldn't make any sense. So we know that our volume of the cylinder has to occur when x is between 0 and 10. But we want to find out the maximum volume of the cylinder. So what we do is we try to find a local maximum between those 2 points, which would be right about here. Now if we draw a line over to our y value from that local maximum, it'll look something like this. And then if we drew a point downward from that local maximum, it would look something like this. So with this being the graph of our volume function, that would mean that this value of x would be the value of x that would give us the largest volume. And then this value of y here would be the largest volume possible, given this volume equation. So if you use the graphing calculator or some sort of graphing function, software or whatever, you could use that and you could find the coordinates of this point. Whatever you use to graph this, if you use it to find this point, you would find that this point has the coordinates 3.33 and 465.4. So that means we maximize our volume equation when x is equal to 3.33. And then our maximum volume of our cylinder would be 465.4. And because every other point is lower on the y-axis or in the y direction, that means that every other x value will give us a smaller volume of the cylinder. And that completes the tutorial on graphs of polynomial functions.